This journey will take you from the farthest reaches of the cosmos, where gravity sculpts galaxies and bends light, to the very ground beneath your feet, where its familiar pull gives weight to your every step. Gravity is not a distant or abstract concept relegated to the ivory towers of academia. It is a palpable, pervasive force that affects each and every one of us, every moment of our lives. When discussing gravity, one cannot overlook the role of space-time, an elegant, four-dimensional construct that unifies the three dimensions of space with the singular dimension of time. If we are to truly appreciate the essence of gravity, it is imperative to develop an understanding of the very stage upon which it performs, the fabric of space-time. What is space-time? In classical physics, space and time were considered separate entities, each with its own set of laws. However, the advent of Einstein's theory of general relativity revolutionized our understanding, proposing that these dimensions are inextricably intertwined. Space-time is not merely a backdrop, it is an active participant in the phenomena we observe. Imagine a vast, cosmic tapestry that is not static but dynamically influenced by the presence of mass and energy. The geometry of curvature. Visualize, if you will, space-time as an elastic sheet. When a massive object, like a star or planet, is placed upon it, the sheet curves around that object. In this model, the object's mass determines the depth and expanse of the indentation or curvature it creates. The Earth orbits the Sun not because it is being pulled by the Sun, but rather because it's traversing a curve in spacetime created by the Sun's mass. Gravitational waves, ripples in the fabric. When massive celestial bodies like neutron stars or black holes collide, they send out ripples in the fabric of spacetime. These are known as gravitational waves. Detected only recently, these waves confirmed another aspect of Einstein's theories and opened up a new avenue for astronomical observation. They offer us a different means of seeing the universe, through the fluctuations they induce in spacetime itself. The influence of energy. It's not just mass that can curve space-time, energy plays a role as well. According to the principles of general relativity, even light, a massless particle, can experience the curvature of spacetime due to its energy content. This leads to phenomena like gravitational lensing, where the path of light bends as it passes close to a massive object. As we approach the 21st century's third decade, our understanding of spacetime remains far from complete. Concepts like dark matter and dark energy challenge our grasp of spacetime's properties. Furthermore, the principles of quantum mechanics, which excellently describe the subatomic world, currently stand at odds with the theories of relativity, leading to an ongoing quest for a grand unified theory that can reconcile these disparate realms. In a universe governed by laws and principles, the concept of a cosmic dance serves as a poetic metaphor that illustrates the delicate, orderly, and indeed, almost choreographed movements of celestial bodies. This phenomenon is far from a random assortment of actions, rather, it's a complex system of interactions guided by the gravitational forces at play. In this grand ballet, gravity is the choreographer. It dictates the steps each celestial dancer must take, guiding planets around stars, moons around planets, and even stars around galactic centers. Each object in the cosmos, irrespective of its size, obeys this choreographer's commands, moving in paths that fulfill the requirements of gravitational interaction. Just as a dancer would make a pirouette or leap across the stage, planets make elliptical orbits, and galaxies spiral, all under the meticulous direction of gravity's unseen hand. Orbits are essentially the routines executed in this cosmic dance. A planet does not simply revolve around a star, it follows a precise path shaped by both its own mass and the mass of the star it orbits. The beauty of these orbits is that they are self-sustaining, driven by a balance of kinetic and potential energy. The celestial bodies are in a continuous dance, sustaining their momentum and preserving the balance that keeps them from crashing into each other or spiraling off into the abyss. Even celestial phenomena like comets and meteors, which seem to make guest appearances, adhere to this universal routine, captivated by the pull of larger objects as they traverse the cosmos. Massive events like supernovae, black hole mergers, and the formation of new celestial bodies introduce new steps to the existing routine. These events can even send ripples across the fabric of space-time, altering the dance patterns of distant celestial objects and thereby leading to an ever-changing, ever-adaptive performance. In the grand spectacle of the universe, time dilation acts as the unseen choreographer, a subtle director that affects not just the movement of celestial bodies but the very flow of time itself. Though this might sound like a topic from the realm of science fiction, it is a concept grounded in the rigorous mathematics and empirical observations that define Einstein's theory of general relativity. Albert Einstein forever changed our understanding of time and space when he introduced the theory of general relativity in 1915. In this framework, he demonstrated that time dilation isn't a mere curiosity, It's an integral part of how massive objects interact with the space-time fabric. The greater the mass and the closer an object comes to it, the more time itself will slow down relative to observers situated farther away from the mass. Picture a vortex on a dance floor. As dancers approach the vortex, their movements seem to slow down relative to those who are farther away. The closer they get, the slower they appear to dance, until they appear almost frozen in time to observers at the edge of the dance floor. This slowing down is analogous to time dilation. As you move closer to a massive object, time slows down when compared to a region of weaker gravity. Time dilation isn't merely theoretical, it has practical applications and has been experimentally verified. For example, the clocks on Global Positioning System, GPS, satellites run slightly faster than clocks on Earth due to the weaker gravitational field at higher altitudes. Engineers must correct for this discrepancy for the GPS to function accurately. In another instance, physicists using highly sensitive atomic clocks have observed that time passes more slowly for a clock placed at a lower altitude compared to one at a higher altitude. In celestial terms, time dilation has consequences for phenomena like black holes and neutron stars. In the vicinity of a black hole, gravitational forces are so immense that time dilation effects become extreme. If one were to approach a black hole, an observer far away would see them slow down and eventually freeze in time as they near the event horizon, although the person falling into the black hole would experience time normally. What time dilation teaches us is that time is not a fixed entity but a malleable dimension, influenced by gravity. It adds another layer to the already intricate choreography of celestial bodies. Planets, stars, and galaxies don't just dance through space, they also dance through time, each at their own unique tempo set by their gravitational environment. Each movement affects the other, whether through minute perturbations in an orbit or the dramatic events of a galactic collision. In summary, the term cosmic dance is far from a casual metaphor. It captures the essence of the intricate and ordered manner in which celestial bodies interact, a spectacle directed by the invisible but omnipotent choreographer, gravity. As we delve deeper into understanding this grand performance, we come closer to comprehending the enigmatic laws that govern our universe. In the universal opera, if gravity serves as the conductor and space-time as the stage, then black holes are undoubtedly the maestros of cosmic drama. These enigmatic celestial entities exert a gravitational pull so intense that nothing, not even light, can escape their clutches once past a certain point known as the event horizon. The mystique surrounding black holes makes them not just objects of scientific inquiry but also captivating phenomena that challenge our very understanding of physics and the universe. A black hole is usually born from the violent death throes of a massive star. When such a star exhausts its nuclear fuel, it can no longer counteract the pull of its own gravity. As a result, it collapses, and the ensuing supernova explosion can result in the formation of a black hole. The most defining feature of a black hole is its event horizon, a sort of point of no return beyond which escape is impossible. Once any object crosses this boundary, it becomes part of the black hole's singularity, a point of infinite density at the center. The event horizon acts like an impenetrable curtain, behind which the rules of conventional physics break down, giving rise to speculative theories and mind-bending possibilities. In the cosmic ballet, a black hole acts as a sort of gravitational siren, irresistibly drawing objects toward it. However, its influence isn't just one of entrapment, it's one of complex orbital dynamics. Objects that don't venture too close can maintain stable orbits, performing a perilous but consistent dance around the black hole, much like how planets orbit stars. This relationship is governed by the same principle of time dilation, making the vicinity of a black hole a realm where time itself bends and twists. Black holes present numerous paradoxes that baffle scientists, one of the most famous being the information paradox. This arises from the principles of quantum mechanics and the idea that information entering a black hole is lost forever, conflicting with the laws of quantum physics. However, theories like Hawking radiation propose that black holes can emit energy and eventually evaporate, potentially offering a solution to the paradox. This theoretical emission is like a soft whisper in an otherwise deafening cosmic symphony, subtle but immensely significant. Some speculative theories propose that black holes could serve as bridges to other universes or dimensions. While these ideas are largely the subject of mathematical conjecture and speculative physics, they contribute to the allure surrounding these mysterious entities. It's as if each black hole might be a backstage passageway to an entirely different performance of cosmic ballet, with its own rules and dancers. Recent advancements in technology have allowed us to photograph a black hole for the first time, pushing the boundaries of what we know and what we can observe. However, despite such milestones, black holes remain cryptic puzzles. Gravity, a force most people take for granted, is perpetually shaping Earth's physical landscape, weather patterns, oceanic behaviors, and even biological systems. While the spectacle of celestial bodies orchestrated by gravity often steals the spotlight, the influence of gravity on our terrestrial existence is equally captivating and essential. Gravity is the silent architect behind the Earth's formation. About 4.6 billion years ago, a gravitational collapse within a giant molecular cloud led to the formation of our solar system. As particles clung together through gravitational attraction, Earth gradually accreted from a cloud of gas and dust, transforming over eons into the rocky planet we inhabit today. In this formative period, gravity acted as the binding agent, turning disparate particles into a coherent whole. One of the most visible impacts of gravity on Earth is the phenomenon of tides. Governed by the gravitational interplay between Earth and its moon, as well as the Sun to a lesser extent, tides serve as a rhythmic pulse for oceanic life and coastal ecosystems. The gravitational pull of the moon creates a bulge in the Earth's oceans, leading to high and low tides. This cyclical ebb and flow have far-reaching implications, affecting marine biology, weather patterns, and even human civilization through naval and fishing activities. Gravity's influence extends upward into the sky, holding Earth's atmosphere in place like an invisible protective shield. In the absence of sufficient gravitational force, these gases would escape into space, rendering Earth uninhabitable. Gravity also impacts Earth's geology, contributing to the movement of tectonic plates and thus playing a role in phenomena like earthquakes and volcanic activities. Additionally, gravity affects the circulation of ocean currents and air masses, directly influencing climate zones and weather patterns. For example, the Coriolis effect, a result of Earth's rotation and gravitational forces, plays a significant role in the direction and formation of wind patterns. Gravity even influences biological processes. For example, plants grow roots downwards into the soil and stems upwards towards the sky, guided by gravity. Similarly, human physiology has evolved to function optimally in Earth's specific gravitational field. Muscle strength, blood circulation, and a host of other factors are all influenced by gravity. Experiments in microgravity environments, such as aboard the International Space Station, have revealed that long-term absence of gravity can lead to muscle degradation, bone density loss, and other health issues. Human civilization has also learned to work with, and sometimes against, gravity. Everything from the construction of skyscrapers to the development of transportation systems has to account for gravitational forces. Our mastery of mechanical physics, a subject intrinsically tied to understanding gravity, has been instrumental in shaping the technological advancements that define modern life. Gravity's terrestrial influence is so pervasive that it touches every aspect of our existence, from the geophysical to the biological. So, the next time you look up at the night sky or simply drop an object to the ground, ponder for a moment about the remarkable force you've just witnessed. We invite you to subscribe to our channel for more explorations into the fascinating realms of science and philosophy. Thank you for watching. Please subscribe to our channel for more exciting content.